All right, January 18th. Last time you were here, our big conceptual leap forward was, instead of looking at a generic vector as v equals a magnitude and an angle, what we did was we looked at our vector as two component vectors, Vx and Vy, and our angle here was there. And we gave you equations that you can utilize to break this into, I guess we could present it like this. And so instead of thinking of our vector as one arrow that points at a given direction, quite literally, this vector here doesn't even exist anymore. And what we do is we think of it as the sum of these two. Now, how's that going to help us? Today we're going to make the cool leap forward, hopefully, because what we're going to do is we're going to talk about how does this help you when it comes to adding vectors together mathematically. Now, in order to do this, I am going to create a problem, a simple vector addition problem that is totally going to reside in the first quadrant. And what we're going to do is we're going to make the sketch of it, but then we're going to make the sketch of it graphically like this, but then we are going to take that picture and we are going to break it down like this and see if we can make some connections. Okay? Now, in your master list of vectors, as I looked at it, you only had two first quadrant vectors, A and E. So we're going to go ahead and pretend that we are going to take A plus E. Now, I'm not going to go through the way they would do this in math to show both of them and then move them around. I'm just going to do it the way that if I gave you this as a graphical problem, you would go ahead and do it. Now, A points at 31 degrees and E points at 77 degrees, so I know I'm kind of going off in that direction. So I'm going to start my coordinate axes down here, and A would be right there, and then in a different color, I'll go ahead and do orange. E is a little bit longer and it goes at 77. So remember, the idea is, and I'll do this in red, we would pretend that we have a brand new set of coordinate axes there, and then we're going to go 77 is off in this direction and it's a little bit longer. So we'll go there and we'll say, there's my E. All right? Hopefully, so far, so good. Now, our answer, quick reminder, what's our answer called? What? Resultant. You guys paying attention? Sarah hasn't even been here. She's on top of it. Awesome. Okay? And I'm going to put my answer in blue here. And to make it, because that's kind of a long kind of a long straight line for me to draw. I'll go ahead and cheat here with my meter stick. We would go from the beginning of our chain to the end. All right. This is my R. Which way does it point? Okay, it points off in this direction. So it goes from the tail of the very first vector up to the tip of the last one. All right, so here's our problem, all done. But we want to do this mathematically. So, should we go volunteers? Okay. Could I get somebody? I'm going to need 3 people. I want somebody to come up and in black break this into its horizontal and vertical component. So just like draw it as a horizontal and vertical component here. All right, Liam. If you're going, what the hell? We'll see. Okay, and go ahead and label that one AX, and that one would be A. Now, also, give me an arrow tip on each one. Which way would AX point? And which way would AY? Perfect. Okay? Thank you. All right, we got A broken down. Where's my orange? Somebody want to come do E for me? Okay, Nikita. Yeah, bring that guy straight down. Okay, now I'm going to have you change one thing. What letter is this going to be? What letter is the orange vector?
Oh, E.
Yeah. So make that an E.
That's in here.
Yep. Perfect. All right. Thank you. All right. Last one. R. Somebody want to come break off? Okay, Reese. Now, I am going to say, don't if you have to, if you're like, I'm right on top of that one, just put it right below that so we can distinguish the different colors.
Gosh, I got it.
Yeah, that's fine. Hopefully by this time, conceptually, you guys are like, oh, I know what you're getting at. All right?
Oh, that was okay.
That's fine. Okay, perfect. All right. Now, I am going to tell you that every single thing that you need to kind of move forward in this process right now is in this picture. Okay? And the thing to remember is, which color is our answer?
Blue.
Blue. So basically, I want to be able to say 2 things about my blue vector. I want to be able to say how long is that, and what angle does it point at? Okay? Now, can somebody kind of throw out anything, any connections you might be making in the picture? Okay.
Rx equals Ax plus Ex. And
Bingo.
then, yeah, Ry is Ay plus
this Rx goes from here to here. AX goes from here to here. EX goes from here to here. So in this picture, Rx equals, this is where I'm going crazy with colors. AX, and I'm going to go ahead and use this for plus, where's my orange? EX. And RY equals AY plus EY. Okay? So, now this thing that I'm calling RX, RX represents the X component of my resultant. I gotta do a different rule here. All right, now I'm gonna have to go a different color here, going green. All right, this is the part where we're gonna say, what I write down here, you can apply in any vector addition problem. To get the horizontal component of your resultant or your answer, all you have to do is add up all of the horizontal components of all the vectors that you're told to, that you're adding together. So if I had your vector chain that had 5, you would simply have a mathematical expression here that would have 5 X components being added together. Now, I'd like to graphically illustrate this for you, but I'm just going to throw out this question first. If someone goes, wait, if you keep adding them up together, aren't they just going to keep getting bigger and bigger and bigger? What's your response to that? No. Give me the part that comes after that. As in, why not?
The sign could be different.
Correct. If you did your vector resolution properly, remember anything that points this way will have a negative sign at it, or anything that points down would have a negative sign. So again, this goes back to our net force concept. When people draw free body diagrams and they look at them and say, well, I'm going to take this one and this and subtract from this, and that drives me nuts. Because the concept is you always add everything together all the time. And things will just have positive or negative signs if you've done that properly, so that any idea of subtraction automatically takes care of itself, because as you're adding all of the pieces together, some of them, because they point in towards the left or down, will have a negative sign. And then for the vertical component, you get your vertical component of your answer by simply adding all of the vertical components of the vectors you're adding together, which, again, AY goes from here to here, EY goes from here to here, but you add them together tip to tail, and they go from here to here, and that is your RY. So, I am doing this in a first vector or first quadrant problem because it's easiest for people to see. I may do a quick sketch for something that kind of goes, overlaps quadrants, but only after we do the real simple one. Okay, so at this point, I call this step 2. Step 1 was break all your vectors into their components. Step 2 is combine all of the component vectors in the 2 dimensions of your problem. Now, step 3. I want these 2. Can someone tell me how am I going to get this one? Based on what we have just finished doing. Okay, Liam.
Solve for the hypotenuse.
Very good. In blue, what kind of triangle do we have?
Right.
Yeah, we didn't put all of the right angle symbols in here, but we covered that last time, that one of the things that is special about the relationship between your x component and your y component is that they are at right angles to each other. So these are all right triangles. So now we have a right triangle, and essentially once we get to this Rx, Ry, I could go ahead and erase the orange and the black because we're done with those. We have this thing in blue. Sometimes I'll refer to it as the answer triangle. Once you have the two components of your answer triangle, it's a right triangle. And these are the two legs. So how are you going to figure out that hypotenuse? Somebody? The Pythagorean theorem. So now just watch this for the moment. Can somebody give me how would you express your Pythagorean theorem expression for our blue triangle? Using stuff that's on the board. Nobody's getting this.
Do you want it with the R's or like with the A's and the E's?
That I want it with the R's.
Rx squared plus Ry squared equals R squared.
Now, what is it that I want out of this?
R.
Okay, and so what am I going to have to do to get R all by itself?
Just take the square root of both sides.
Okay, so if I take the square root, and here's my general rule again, what will the other side look like?
Rx plus Ry. Oh,
No.
no.
Because you said take the square root, right?
Yeah.
But why can't I just nix those squares?
Oh.
Because we're adding them. So this is an expression that people are like, oh my God. Okay, now we've talked about, well, when you take a square root, you can get a positive or a negative. What are you going to do here? It'll always be the positive, because the way that we manage the concept of sine is through the angle. Okay, we're making progress. Okay, this is step 3. So what's our one missing piece?
Finding the angle.
Finding the angle. Anybody know how we're going to do it? This is the part where we definitely go with the first quadrant situation first because it's easiest. No, nothing? Okay, should I just give it to you? What are the names of the function? Because most of the time, if we want to play with triangles and angles within the triangle, we talk about, we will use the angle to get lengths on the sides. What is the kind of type of function that we use when we have the sides and we use the sides to figure out the angles inside the triangle?
Tangent. Theta.
Close.
Law of sines.
What?
Inverse.
Inverse tangent. Because we have the two sides and we want the angle. So when you talk about sine, cosine, and tangent, what you're talking about is using an angle to figure out sides of a triangle. If you are going to use the sides of a triangle to figure out the angles inside of it, you want to do the opposite that sine, cosine, and tangent do, and those are all called inverse functions. Anybody know the proper math term for them?
Arc.
Arc. So when they talk about arctangent, arc cosine, arc sine, that is the same thing as, and I'll go ahead and put that there because most people are more comfortable with this and saying it's inverse tangent. Now, remember, this does not equal 1 over tangent. This is like the opposite thing that a tangent function does. Now, just to throw this out for calculator usages, some calculators do not do this. You will see that. That is arctangent. That is the same thing as tangent to the -1. Okay. So now, what do we have to put here? I'm really drilling you on your trigonometry now. Anybody know what's going to go in here? No. A fraction. What goes over what? Let's just say we're talking about arctangent to begin with.
RY over
What goes over what in terms of the sides of the triangle?
RY over RS.
Well, before we get to the specifics of the picture, what is tangent?
Sine over cosine.
If you're doing it trigonometrically, but if you're doing it by the sides of a triangle,
Opposite over adjacent.
opposite over adjacent. This is the angle we want. What is the opposite side from that? The RY. What is the adjacent side? RX. Okay? And this equals our theta. Okay? Now, here is where we run into our problem. Now, the rule, I am going to do this. Oh, actually, I'm going to do it this way. Because what we really want is the theta. So I'm going to couch it this way. This is going to be some beautiful math here in the last 10 minutes. I did this as a first quadrant problem because if you process this on your calculator, everything would work out perfectly. Oh, you know what? Screw this. I'm not going to try and cram this in 10 minutes. Okay? We will go ahead and end it here today. And tomorrow, what we are going to do is we are going to explain to you why your calculator, as beautiful as a calculating machine as it is, it has a level of stupidity. And you are going to need to determine a theta that potentially could go from 0 to 360, and your calculator can't do that for you. But you can take what the calculator will give you and get the right answer if you understand why your calculator really can't do that in the first place. And it goes into a beautiful discussion of inverse functions. So we're going to talk about more math that you guys have had exposure to. Anybody remember the concept of one-to-one and inverse functions? Okay, if you remember that, and the truth is you will hardly ever have to really worry about it, but this is a place that you got to worry about it, and it comes into play. But I'm going to give you a set of rules so that you'll know how to deal with it. All right, that's my teaser for tomorrow. Just make sure you come back. Okay.